Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on Pigeonhole Principle, lecture number 2, in which I will prove some theorems and solve some problems on Pigeonhole Principle. Now we prove Theorem 1 statement. If r is greater than equal to 2 is an integer, and if n multiply r minus 1 plus 1 objects are placed in n boxes, then there exists a box with at least r objects. Now we prove this. Proof. Given that number of boxes equal to n, number of objects equal to n multiply r minus 1 plus 1. If possible, let every box contains less than r objects, that is, sum of the boxes contain r minus 1 objects and remaining boxes contain less than r minus 1 objects. Therefore, sum of maximum number of objects in all boxes equal to number of boxes n and maximum number of objects in each box be r minus 1. So this will be n multiply r minus 1. Let this is number 1, this is number 2, and this is number 3. Therefore, 3 contradicts with 2 because total number of objects is n multiply r minus 1 plus 1. Here maximum number of objects be n multiply r minus 1. So this is less than this number of objects. Hence our assumption is wrong. Therefore there exists a box which contains at least r number of objects. Proved in other way. Let one box contains r number of objects and remaining each of n minus 1 number of boxes contain r minus 1 number of objects or less than r minus 1 number of objects. Therefore, sum of maximum number of objects in all boxes equal to, in one box we have r number of objects, r in one box, and remaining n minus 1 boxes, maximum number of objects in one box is r minus 1, r minus 1. This equal to r plus n into r minus 1 minus r plus 1. This r cancel, and this is equal to n multiply r minus 1 plus 1. This is number 4, which is same as number 2. Therefore, there exists at least one box which contains r number of objects. Proved. Now we prove theorem 2. Theorem 2 is known as generalized pigeonhole principle statement. If there are n pigeons and m pigeonholes where n is greater than m, then some pigeonholes must contain at least, this is n minus 1 by m, this is greatest integer function, plus 1 pigeons, where this under bracket x denotes the greatest integer less than or equal to x. Now we prove this. Since given that number of pigeons equal to n and number of pigeonholes equal to m, let this is number 1, this is number 2, where n is greater than m. If possible, let each pigeonhole contains less than, this is greatest integer function n minus 1 by m plus 1 pigeons. Therefore, sum of the pigeonholes will contain less than this, means greatest integer function n minus 1 by m pigeons, and each of remaining pigeonhole will contain less than this greatest integer function n minus 1 by m pigeons. Therefore, sum of maximum number of pigeons in all pigeonholes will be, number of pigeonholes be m multiply greatest integer function n minus 1 by m, and this is less than equal to m n minus 1 by m, this is equal to n minus 1. Let this is number 4. Here in 1 we have number of pigeons equal to n. Here maximum number of pigeons in all pigeonholes will be n minus 1. So therefore 1 and 4 contradict with each other. Hence our assumption is wrong. Therefore some pigeonholes must contain at least greatest integer function n minus 1 by m plus 1 pigeons. Proved in other way. Let one of the pigeonhole contains this greatest integer function n minus 1 by m plus 1 number of pigeons, and each of some pigeonholes contain greatest integer function n minus 1 by m number of pigeons, and each of remaining pigeonholes will contain less than greatest integer function n minus 1 by m number of pigeons. Therefore, sum of maximum number of pigeons in all pigeonholes equal to, in one pigeonhole number of pigeons equal to this greatest integer function n minus 1 by m plus 1 in one pigeonhole number of pigeons, and remaining number of pigeonholes m minus 1, maximum number of pigeons in these holes greatest integer function n minus 1 by m. This equal to greatest integer function n minus 1 by m plus 1 plus m multiply greatest integer function n minus 1 by m minus greatest integer function n minus 1 by m. this and this cancelled, and this is less than equal to 1 plus m multiply n minus 1 by m. This is greatest integer function which is less than this. This is equal to 1 plus m cancel, here n minus 1 plus 1 minus 1 cancel. This is equal to n. Let this is number 5, which is same as 1. Therefore, there exists at least one pigeonhole will contain greatest integer function n minus 1 by m plus 1 number of pigeons. Proved. Now we prove theorem number 3 statement. If a pigeons are more than k times of pigeonholes, then some pigeonholes must contain at least k plus 1 pigeons. Proof. Let number of pigeons equal to n and number of pigeonholes equal to m, given that number of pigeons are more than k times number of pigeonholes, means n greater than km. This is number 1, this is number 2, this is number 3. Let n equal to km plus r, where r is greater than equal to 1, less than m. This is number 4. Since by generalized theorem of Pigeonhole Principle, we have there exists at least one pigeonhole which contains n minus 1 by m greatest integer function plus 1 pigeons. This is number 5. Using 4 in 5, we get there exists at least one pigeonhole which contains, in place of n we write km plus r, km plus r minus 1 by m greatest integer function plus 1 pigeons equal to km by m plus r minus 1 by m, greatest integer function, plus 1 pigeons, is equal to k plus r minus 1 by m, greatest integer function, plus 1 pigeons. This is number 6. Since r is greater than equal to 1, less than 2m, implies that r by m less than 1 and greater than 0, implies that r minus 1 by m greater than equal to 0, less than 1. This is number 7. Using 7 in 6, we get k plus r minus 1 by m, greatest integer function, plus 1 equal to k plus 1. Since k is a positive integer, this is number 7. Therefore, we get that there exists at least one pigeonhole which contains k plus 1 number of pigeons. Proved. Now we solve a problem. Problem is, if 30 magazines contain a total of 61,324 pages, then one of the magazine must have 2045 pages. Now we have to solve this. Given that number of magazine equal to 30, we may compare this with pigeonhole, number of pigeonhole, and number of pages equal to 61,324. This may be compared with number of pigeons. Therefore, there exists at least one magazine, means one pigeonhole, which contains 61,324 minus 1 by number of pigeonholes 30 plus 1 pigeons, means here pages. This is pigeons, and this is equal to 61,323 by 30, greatest integer function, plus 1, and this is 2044 and 3 by 30 plus 1. This is not an integer, so This will be equal to the greatest integer less than or equal to this value, which is 2044 plus 1. That means 2045 pages. So our problem is solved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.